Okay. Well, good morning or good afternoon, everybody. Allow me to formally introduce our distinguished guest, Professor Witold Pedricz. He's a professor, chair, and researcher at the Alberta University in Canada. He's an expert in computational intelligence with application in software engineering, pattern discovery, knowledge discovery, pattern recognition, and many other areas. He will explain in detail in a few minutes. Well, the aim of this meeting is, well, first of all, to listen to Professor's lecture and take advantage of his knowledge and his experience, and then to generate a discussion, to exchange ideas, in order to discover some common areas of interest and potential points of collaboration. We wish in the near future to be able to define some joint projects, some collaborations. Okay, I think you can proceed with your lecture.
Very much. Thank you very much. I'm definitely very much pleased being here, and I'd like to express my thanks for giving me this opportunity to meet everybody today and talking about my research. This meeting is under the auspices of this distinguished lecture program of IEEE Computational Intelligence Society. I think the logo of the society is shown here, so definitely it is one of the IEEE societies that tries to bring all these ideas of computational intelligence into advanced research, as well as convert this research into some interesting and useful practical applications. And I do hope that my talk today could be of some interest to you. I understand that people are coming from different research areas, have their own kind of research directions. What I'm going to discuss today is related to aspects of computational intelligence and granular computing. I sort of use the title granular fuzzy models because I'd like to use fuzzy models as one of the examples in the investigation of the principles of granular computing. However, I do hope that our discussion, our presentation today, has some general underpinnings that you can find of some interest in your own research area. Interestingly enough, this research in computational intelligence and granular computing creates a relatively new development. So in this sense, I do hope it could also trigger some interest if you are looking at some potential research directions in your future work. And I'd like to promise you that there won't be not too much mathematics. I know that formulas are always just create a certain distraction. I would like to really stick to some conceptual developments, just to offer some interpretation, offer some insights into the underlying concepts. And if you are interested in some detailed discussion of the mathematical nature, which I think does exist when we are handling these problems, but I would be more than happy to provide you with some additional reading material. There have been done a lot of research in this area just recently. So here's my email address, and I'll be happy to answer any questions that you might have maybe a little bit later after the seminar. I know that sometimes questions are coming up instantaneously, some questions are coming up after some studying. And you are more than welcome to make a copy of these PowerPoint slides. They are on this computer, so there is nothing like copyright, which I don't believe in. Okay, and obviously I would be very happy to entertain any discussion, any questions that you might have during my presentation. So do not hesitate to ask questions during the talk, okay? I know that sometimes people are so shy, people are so eventually, you know, too polite, put it this gently, that they say, okay, let this guy talk and I may eventually ask a question at the very end. No, don't do that. Let's get into some more interaction, more sort of dialogue-like presentation, okay? So here's just the agenda of my talk. Yeah, agenda of my talk. I would like to start with some motivating observations. That's probably will be done in the context of fuzzy models, as this is just, in my opinion, quite compelling example. And then I'd like to talk about the ideas of granular computing. And you can find that these ideas are essentially, in one sense, quite new, but in some sense they are quite old and quite intuitively appealing. So you can find that there are just really two aspects to this entire area, and essentially my intention would be just to look at some of the principles of granular computing, okay? What are the principles? What are the fundamentals? How can I really take advantage of this concept? How could I do consecutive processing? And then I'd like to talk about some more specialized aspects of fuzzy models by looking at granular hierarchies of fuzzy models and come up with some conclusions. Let me start with something that is obvious, and it comes from one of the researchers in statistics. I think he was doing research in those statistical models, and something that is evident to all of us, no matter which area we are coming from. There are no ideal models. There are no ideal models. I think you can build complex models, and you know that you are always striving to come up with something that is ideal, something that mimics the reality to the highest possible extent. And from our practice, we know that this is really just a very desirable goal, but we have to be realistic, okay? So my question, or sort of my, this opening sort of statement coming from Box is really well rooted when we come to this area of fuzzy modeling. I suppose when we are talking about fuzzy models, and I can presume that some of you are very well familiar with fuzzy sets and fuzzy models, rule-based models, we can see something interesting, that when fuzzy models appeared, they became quite innovative, and there have been a lot of design practices. But one question that came to my mind after a while, looking at the history, was the fact that fuzzy models, no matter how they were designed, how were they developed, they followed a certain general scheme. In other words, yes, we try to encapsulate knowledge about the system in terms of fuzzy sets, for instance, in terms of rule-based architectures, but at a certain point, the entire design scheme followed this type of line of thought, that we had data, and we created fuzzy model, and we evaluated the fuzzy model on the basis of its numeric manifestation. So in other words, we had a process of transforming fuzzy sets into some numeric quantities, and this performance index really just implied that when we do some optimization, then this model could be improved. Obviously, there are some limits to the quality of the model, because you are looking at the number of rules, and you try to really make the model more sort of, interpretable. So with regard to the first observation I made, I would like to look at a slightly different look, or try to look at a slightly different design strategy. Well, let us admit that we created a fuzzy model, and we want to make it more in line with reality. We'd like to make it more sort of in rapport with the data. How can we do that? Well, and the philosophy here is the following. hold on, don't make this model more and more complex, but try to envision that this model could be augmented by bringing a concept of information granules. I'll be talking about this in sort of at the later stage of my talk. So in other words, we are going to look at the fuzzy model we constructed, and we bring the concept of information granules to augment the model and produce a so-called granular model. And this model is contrasted with the data, and it's kind of confronted with the data, but the evaluation of the quality of this granular model is carried out in terms of some new performance indices. And this entire line of thought is essentially not only applicable to fuzzy models, but it's applicable to any model that we developed in the past. So in other words, a model that has been inherently numerical, okay? So this is the kind of preamble, the starting point of my discussion. And now I'd like to switch on to the ideas of granular computing, because that's really the core part of my presentation today. So what do we mean by granular computing? What do we mean by information granules? And what do we mean by some principles of granular computing? So when we are talking about information granules, obviously the first question that comes to our mind is the following. What do you mean by information granules? What is this sort of idea of information granules? And I don't want to be too formal now. I would like to appeal to your intuition. You have seen, you've been using information granules every day. Because the way how we perceive the world, how we organize knowledge about our surrounding environment, how we process this knowledge, how we communicate this knowledge, all of these activities are carried out at a certain level of abstraction. What I have in mind is the following, that we never think, we never reason in terms of numbers. We use concepts, we use some entities that are more abstract. So, not pretending to offer you any formal definition of information granules, I would like to refer to the definition that goes like this. Namely, by information granules, we can think or we can regard just entities that are composed of elements that have something in common. What do we mean by something in common? That the elements that exhibit some similarity, the elements that exhibit some functional closeness, the elements that exhibit some spatial closeness, spatial neighborhood, the elements that have some temporal resemblance. Well, notice that you are developing, you are forming information granules every day. You are looking at digital photography, you are not seeing millions of pixels, you are seeing some object, you are seeing some entities, you are seeing information granules. What have you done? In a subconscious manner, you created, you look at the image and you identified elements that are positioned close to each other and exhibit some resemblance. For instance, elements that have a similar intensity of color, they have the similar level of brightness, they exhibit similar texture, and so on and so forth. And you can give me millions of examples, because the way how we perceive the world is based on abstraction. We look at the problem from a certain perspective. Yes, please. Yeah, maybe I think there is another microphone, which probably we can keep it somewhere in the sort of close to the audience, so then
Okay, and my question is probably common or shared by the rest of the present. I know something called clustering. Clustering is basically the same. So, when we are clustering, traditional clustering or not, we can use any distance. But aren't we doing granules as you say, or this is just one granule, one atom for you?
So that's one of the possibilities. I mean, when you are talking about clustering, and I think it's very beneficial here, we are really talking about some algorithmic approach to build information granules. But I think I'm starting with the concept itself, and then once we have this sort of understanding of information granular, then is the next question how we're going to construct, and clustering could come here and does come as one of the very prominent algorithms, categories.
Okay, this is one approach, but we can...
Well, this is, I would say, information granules are some concept. Now, how you're going to establish these information granules, then you are going to the sort of, to this layer of algorithm, okay? But before we get into clustering, we have to really confine ourselves to a certain formalism in which information granules are going to be described, okay? So this is a very legitimate, very relevant question, and I'm going to address it at the sort of slightly later stage of my talk.
Second question is about fuzzy. You are speaking about fuzziness, and there's a recent type of fuzzy processing, that is fuzzy set type 2.
Yeah.
Are you meaning there one type of or both types of fuzzy?
Oh yeah, that's something that I think is related to the landscape of information granules. So I'm going to sort of look into this type 1, type 2 information granules. So that's again a very good point that I'm going to jump just in a moment. Okay, next slide. So here is an interesting observation. In 1985, in one of these AI conferences, there was just a paper that stressed the issue of abstraction. There was the paper that sort of says as follows, that our ability to conceptualize the world at different granularities is really crucial to our intelligence and flexibility. And that's what happens. We create information granules in such a way that allows us to capture the essence of the problem, okay? So that one certainly speaks to this abstraction aspect, okay? Now, if we look at any map, you are doing some granulation. You are sort of relying on information granules. You are looking at the problem, at the map from a certain distance. So for instance, I'm looking at North America, but I'm interested, for instance, in something like the province of Alberta. So I'm getting closer. I'm getting closer if I'm interested in the city. So you see that this is the level of abstraction that we can switch in between. It depends on the problem we are solving, okay? Here's another example. You have a lot of data, and that's something that we are seeing every day. Now imagine that you want to come up, Oh yeah, of course, yeah.
I'm sorry. You were talking about granules that have entities of similar characteristics. Those entities can be in two different granules, like...
No, if I'm talking about information granular, I'm naturally bringing some elements that exhibit some closeness. So for instance, some elements that have similar characteristics. So this is just elements put together, they form a certain information granular. For instance, you can talk about concept of high inflation. okay, high inflation. So you are not using the number, but you are using a collection of elements, collection of numbers, and you put them under the same roof that you can call high inflation, okay? So that's the essence. That now, instead of dealing with individual numbers, I'm dealing with a certain concept, with information granular. So then, when it comes to processing, I'm processing this information granular as a single entity. And now, when I'm going through some maybe process of reasoning, then I'm using this information granular to communicate my findings to the decision maker or to the external world in general.
So if that element belongs to a granule, cannot belong to another granule, or can it?
It depends. It depends what type of formalism you decide to choose. If you are talking about set theory, obviously in set theory, so you say, my information granular is described as a set. That's what we know from our childhood, because it was the way how we learned the word. Is that right? We are taught, here's this example, this example, this example. These elements belong to the concept called car, okay? So in this case, you are right. If I have a concept that is described by an information granular, formalized as a set, yes, it could belong to this set, and it does not belong to any other set, eventually. If I'm talking about fuzzy set, it's a different story, because I admit some degrees of membership. So again, this depends on the formalists, and we have a lot of them, okay? So here's an example. You have the data, and somebody asks you, okay, what could you tell me about, what could I learn from this data? That's really what we want as a part of the agenda of data mining, as the part of the agenda of big data. You want to have this interaction with the user. You are asking, so I have the data, tell me what I can learn out of this data. So notice that I might have a lot of readings of temperature in China, okay? And there's a lot of cities, a lot of towns, so you have a lot of numbers, okay? And you collected this data over, let's say, 1 month. And somebody says, okay, could you give me the summarization? What could you tell me about the temperature in a certain part of China? So for instance, you are seeing that this is an example where you have information granulars. And if you can see, out of this temperature data record, you get this type of statement. Recently recorded very high temperature in southeast China. So notice that in this summarization, I'm not using the numbers. I'm using just information granulars. And granulation of information of my data is carried out with regard to time. So it's this sort of recently statement, recently, well, maybe just recent weeks, recent days, and so on. Then you have this granulation in terms of the temperature. So you say it's very high temperature. So you have an information granular that deals with the temperature, and you are talking about the spatial granulation because you are alluding to this a certain region in China, okay? So notice that here is something that is meaningful to the user. I'm not talking to you in terms of numbers. I'm not giving you some formulas. I'm not giving you just the printout of 5 pages of numbers, but I'm saying, here what we have discovered. So now, this is a meaningful piece of knowledge that you can use. You can take this piece of knowledge and you can make a decision out of it on its basis. So it's something that the knowledge is actionable. You can take an action, okay? And you can find me hundreds of examples. If you have some records of the performance of the company, you can do the same if somebody from the, from the top management asks you, okay, what could you tell me about the situation of the sales in a certain region? Now you are not going to give just, tens of pages of numbers, but you are going to show this in the form of information granulars. So you probably become convinced that information granulars are present everywhere. In other words, this is the way how we perceive the world, okay? So this is really just a very brief summary of what I said so far. You are talking about information granules as a certain vehicle to create abstraction, to support abstraction, okay? And information granules offer you a way to customize the view of the problem. It is user-centric and it's business-centric. It depends upon the problem. There is no one universal granularity. It depends on the problem, okay? You can look at more abstract or more detailed description of reality, okay? So the processing at the level of information granularity is problem-dependent. What I said so far, as you can notice, I have not used any mathematics. And this could be okay for any talk to the business community, to the people in non-technical areas, but we want to do something more. Because we want to take this information granules and we badly need to come up with its representation that we can process, okay? So what you see on the left-hand side of the slide is really concerned what we talk about. It's really just a kind of convincing arguments that speak loudly to the essence of information granules. But those information granules do exist in a kind of implicit manner. But you need something more. You have to take these information granules and you have to make them operational. So then I can describe them and I can process them at the computer level. Okay? And interestingly enough, at this point, we can see that we already witnessed a number of possibilities. There is a plethora of possibilities because from the inception of human race, we are seeing that we use different formulas to construct or to describe information granules. Set theory, fuzzy sets, rough sets, interval mathematics, probability calculus, all of them are examples of formal frameworks in which we we express information granules. Go back to probabilities. Probabilities are examples of information granules such that you are having millions of data points, but you describe them in terms of some probability density functions. So that's the beauty. You have millions of data points, and suddenly you say, it is governed, these data are governed by a probability density function. Let's say Gaussian probability density function. So what you did, you went to a certain level of abstraction. The same you do with fuzzy sets. You form fuzzy set so that you describe the reality. You become not connected to a single number. So now in terms of information granules, as you are seeing, they are different in different formal frameworks. And the first point that I made at the beginning of the talk was granular computing is new. Granular computing is a not sort of discipline. Well, it is odd in the sense that we are seeing a lot of those developments, the formal frameworks, they happen many centuries or many decades ago, okay? They have been on the market, they have been used for a long time and by a large group of researchers. So somebody would say, so what do you mean by granular computing? I think you had these information granules for a long time, you had these formalities. Yeah, here is something new, something challenging, because we are going to establish some fundamentals on how to process information granules irrespectively of the formal framework, okay? So in other words, this granular computing is coherent, unified environment supporting formation, processing, and interpretation and communicating this information granules, okay? So here was this originality where the novelty comes into place, okay? We have to admit, we are standing just on some well-defined formalities. And I'm not saying that this is something new, but we want to find some unified platform. We'd like to ask a question, so what are these formalities or what are these fundamentals that are universal, irrespectively whether you are talking about probability or fuzzy sets or rough sets, okay? And interestingly enough, there is a new development that is going to just happen at the beginning of next year, namely a new journal on granular computing, with the first issue coming up in January 2016. And I would like to highlight this point because everybody is welcome to make a contribution to this research area. So, just moving to the next item, I would like to really focus on the fundamentals of granular computing. What do I mean by that? Is there really any fundamentals that have been established so far? And I think it is the point where I'd like to stress there are some interesting developments, but there are a lot of open questions. I'm not saying that this is something that is cast in stone. It's ongoing research. Namely, I'd like to highlight today 3 items that I think could be of interest. Namely, the way of forming information granular. And this goes under this name of a principle of justifiable granularity. The second one is a treatment of information granularity as an essential design asset. This will bring us back to this one of the slides when I was talking about fuzzy models. I was talking about models that you want to make them more realistic. So they like to really account for discrepancies. Could you sort of handle them? Could you quantify them? Could you sort of capture those discrepancies? Okay? So this is just information granularity as a design asset. And the third one that Daniela was alluding to was the question of information granulars of higher type and higher order that naturally are associated with hierarchical way of processing data and information. Okay? So let me start with the first one, the principle of justifiable granularity. And what is the idea behind this? Well, the idea is the following. If you are going to construct an information granular, how are you going to do that? Well, I'd like to allude to your intuition. So if I am forming a concept, like say, high inflation, or comfortable temperature, or any other concept, why am I doing this? Well, I said you want to get something like a more abstract view and sort of more compact visualization of our reality. But you can ask yourself, what are the requirements so that this information granular comes into existence? Okay? Well, information granulars do not appear in a vacuum. They do not come from nowhere. They are a reflection of our experience, our knowledge about the problem, okay? And they give rise to the concept that we consider to be could be convenient to cope with the problem, okay? So here the principle of justifiable granularity is reflective of this. Namely, we want to form an information granular in such a way that it follows, it adheres to the two quite intuitively compelling criteria, objectives. Just to have an information granular, I need a sufficient experimental evidence. It does not happen in a vacuum. I have to have some experience. I have to have some experimental evidence behind this information granular. And secondly, I want to see this information granular to be what is indicated here, specific enough or to have some meaning, some semantics. What do I have in mind by sort of formulating these two criteria? Well, let me start with a very simple example, namely, consider that you have just a collection of individuals in a certain community and you recorded their age, okay? And now you are a decision maker. So you have those data and you want to make a decision as to investment in this community. Do you need a new daycare? Do you need some enhanced transportation? Do you need some facilities for seniors? Do you need sort of more advanced, specialized healthcare and so on? Now, this is an important decision you have to make. And now you have this data. So the first point is to get a better grasp what these data mean, how you could describe this sort of age of this in this population, okay? Well, and you are not looking at at individual numbers, but you're trying to say, oh, this is a quite young population, or this is a population of sort of medium age, you know, population, and so on. So what you are doing, you are taking this data and you are coming up with an information granular that captures this data. So you are just conveying this piece of knowledge to a decision maker, okay? So now notice that I'm taking this data and I'm forming an information granular. So I like to make sure that my information granular have a sufficient justification in terms of the coverage or representation of the data, and at the same time it is specific enough, okay? Because I have to make a decision upon this. So imagine the situation that I create an interval. This is my information granular. And the interval is from 1 to 110 years. Well, for sure, these data are going to be covered, are going to be embraced by this interval. So in other words, all the data points is going to be included in this interval. So it's a strong experimental support behind this information granular. But this information granular does not have any semantics, does not have any meaning, because you would say, could I make any decision upon this number, upon this information granular? Probably not. I think you can go to some other community, also find the same information granular. So you see that you covered your data, so the first criterion is satisfied, but you start losing semantics, you start losing specificity. Now you go to this other extreme. You say, here is an information granular that is really very much reduced to a single number, okay? So this is a number that you're seeing here, and you can find that probably there is nobody of this age in this community. So I think, what is the experimental support coming with this? But it could have, it's very specific, it's very detailed. So neither of those two sort of, you know, situations are ideal in terms of the description of this concept, of this data in terms of the information granular, okay? So when we try to visualize this, you can see that if we consider that those blue points denote our experimental data, and we want to build an information granular, you would like to see it somewhere in this sort of in the middle. So you'd like to see that your information granular is sufficiently well justified in terms of experimental evidence, but it also is specific enough. So it creates an actionable piece of knowledge, okay? So how are we going to do that? Well, next slide. Well, you really have now to go into some quantification what you want to do. Namely, you have to tell me, what do you mean by coverage and what do you mean by specificity of information granular? And the beauty of this approach is that now you can become more detailed. So in other words, you can say, what do I mean by the coverage that is provided by the information granular? It depends. It depends what formalities you decide to use. If you use an interval, the simplest measure of coverage would be the measure that tells you how many elements are covered by this interval. So that's something that you can see a very simple expression that is shown here. Is that right? Now, what about the specificity? Well, the specificity could be expressed as given by this formula. So what you are doing, you are determining the length of the interval, and you refer to the entire range assumed by this specific value, and you take 1 minus this ratio. So interestingly enough, if you say that the length of the interval tends to 0, then the specificity goes to 1, because it's the most specific information granular. But at the same time, the coverage goes to 0. So you see that if I increase coverage, I'm going to suffer in terms of specificity, and vice versa. Okay, this is for intervals. What about if you use fuzzy sets? You can take the same line of thought, but then you have to rephrase your definitions, because in fuzzy sets you have membership degrees, so you cannot do this simple coverage in terms of the counting, but you can take a so-called sigma count, okay? And similarly for the specificity, you can just use this alpha cuts of the fuzzy set that is used as an information granular, okay? Obviously, one could sort of keep moving with this in more detail, because you can say, why should I use the formulas from the previous slide? I can become more general. Yes, you can do that. You can, for instance, consider that, for instance, instead of coverage, expressed as the cardinality, as the count of elements, including interval, it could be any non-decreasing function of this count. So mathematically, you can make it more sort of sophisticated. The same for the specificity, but here you are going to take a function f2 that is a non-increasing function of the length of the interval, okay? Because the higher the length of the interval, the lower the specificity. So let me look at something that is very simple, an interval as an information granular. So you have experimental evidence, those are those points marked here, and now you can envision that your information granular is an interval that behaves like a piece of rubber material, a rubber band. So now you see that you can take the rubber band and you can stretch it, so the coverage increases, but specificity goes down, as being shown here. Or you can start squeezing this rubber piece of rubber material, specificity goes up, but coverage goes down. So as we are seeing, there are two requirements that are in conflict, and mathematically you can come up with a number of possibilities. Here is one of them, namely you can take those two expressions, you can take the product, and you can find the optimal bound, an optimal lower and upper bound of the interval by maximizing this expression. So again, this is one of the possibilities. And interestingly enough, you can do the same by bringing just weighted data. So in other words, you have experimental evidence, but each data point comes with some weight. So you have these pairs, data point and weight, and you want to build an information granular. This could be done quite easily by changing the objective function you want to maximize. Namely, the coverage has to be modified according to this formula, in the sense that you do the counting of the sum cumulative weight of these data points. And there is another sort of possibility that is a little bit more advanced, because you have the experimental evidence that you want to be captured by the information granular, but you also have some data, some experimental evidence that has inhibitory nature. So these data should not be included in the information granular. So this is a typical example when you are coping with the problem of classification, because you have data that should be included in information granular that describe this specific class, but there are data that should be excluded from this information granular. How can you do that? Well, you have to modify the first part of the formula so that you can account for the data that should be inhibitory, and therefore you are talking about this minus sign here in the formula. So again, there's a kind of underlying mathematics behind this entire process. You can do the same with fuzzy sets. I talk about interval information granulars, but if you have a fuzzy set, you can build a fuzzy set in the same way. So you can see that here's a fuzzy set described by membership function f and g, and I want to do some parametric optimization of these membership functions using the principle of justifiable granularity. And again, the three options, just you have the data, you have weighted data, and you have weighted data that also involves some inhibitory data. And here just sort of more detailed discussion along this line. Now, what I showed you so far is essentially a one-dimensional construct, because I said I have experimental evidence, numeric data, and I'm forming an information granular, okay? So now it's a natural question that emerges. So how are we going to cope with, let's say, multidimensional data? Well, the first approach that we can make is the following, that I deal with one-dimensional data, so I project my data on each individual variable, and then I form information granular, and I combine them by taking a Cartesian product. I'm not saying that this is just the only solution, this is the simplest possible solution, because it does not take into account an interaction between individual variables. Here there's a very important point that Daniela mentioned in her comments, namely clustering. And the principle of justifiable granularity is just the way of forming a single information granular, okay? Clustering, which is a very popular, a very important way of forming information granulars, is about designing information granulars where you want to form more than a single information granular. Here is a single information granular. None of the clustering technique is going to cope with that, because in virtue of the concept of clustering, you are dealing with at least two information granulars. Now, clustering is a general concept, and as I said, it depends on the formalism that you are going to engage in this process. Say, if I'm talking about a method of clustering such as K-means, the result is a collection of information granulars represented in the language of sets. If I'm talking about fuzzy C-means or fuzzy clustering, I'm talking about information granulars that are formed in the format of fuzzy sets. If I'm talking about let's say, rough clustering, that means that the results of clustering are created as rough sets, and so on and so forth, okay? There is one interesting follow-up of this, because if you remember what I said, if I have numeric data and I develop an information granular, I'm really, in essence, capturing following the certain general line of thought, because I'm saying, okay, you have experimental evidence, and I'm representing this experimental evidence not by a single number, but by an information granular. So in essence, you are seeing the following situation, that once you consider the numbers, numeric data, as type 0 information granulars, then the result of this principle is an information granular of type 1, namely an interval, for instance. But imagine that if I have my experimental evidence in the form of type 1 information granulars, so they are not numbers, they are, for instance, intervals, and you again using those pieces of experimental evidence, and you want to form a single information granular, you are forming a so-called type 2 information granular, or so-called a granular interval. So you can see the granular interval is an interval whose bounds, A and B here, are no longer numbers, but they become information granulars. They could be intervals, they could be fuzzy sets, they could be probability density functions. It depends what sort of formally you engage in this entire process. But here's the principle. If I have experimental evidence and I want to form information granula, then my information granula is of type +1 vis-a-vis my original data. So that's really just a follow-up or kind of lesson that we can learn from this principle. Next slide. So that's something what is important. It gives rise to the emergence of information granulas of higher type. So that's something what we can talk about when we are dealing with type 1 fuzzy sets, type 2 fuzzy sets, and so on and so forth. I think type 2 fuzzy sets have been quite intensively researched in the past, and I was a bit hesitant about that, because to me fuzzy sets of type 2 emerged out of nowhere, and I was trying to find a stronger motivation, something that I could really become more convinced. So here's the way of doing. If you have experimental evidence in the form of fuzzy sets, and you are asking yourself, could you describe this experimental evidence by information granulas? The answer is yes, I can do that, but then you have to realize that you get a type 2 fuzzy set. So that's a certain interesting observation. The second principle is about allocation of information granularity. And this is a very simple idea, a very intuitive idea. So let me start with a very illustrative example, please. Imagine that you have data, and you decided to build a model for this data, for this process, for this phenomenon. And you decided to go for a neural network. And no matter how neural network has been created, how you design it, I'm not concerned about that, but it's very likely you never get an ideal model. So my question is, how are you going to improve the quality of the model? Or how are you going to make it more in sort of line of reality? Well, somebody would say, yeah, I'm going to make the model more complex, so I'm going to use more layers, I'm going to use more neurons in the structure. Yes, you can probably get some improvement, but you know that your model becomes overly complex and eventually start losing the sort of generalization capabilities. So here's another line, here's another concept, here's another idea. Why not you stick to the neural network that you have, but you allow the parameters of this neural network to be represented as information granulas. So in other words, instead of having numeric connections, as you can see in the upper portion of the slide, you are going to make these parameters information granulas that are indicated by these small circles on the sort of lower portion of the slide. What does it mean? Well, it means that the result of your neural network is no longer a number, but it becomes an information granula. So that is shown here in a sort of illustrative way as a certain band, just that tries to cover your data, okay? That tries to cover your data. So what I'm doing, I cannot really get the better model, but at least I can try to make it something that is more realistic. I'm going to make it in the form of a certain band, in the certain information granula, okay? Now, how could you do that? Well, you have to allow the parameters to become information granulas. So, I can think this way. Imagine that somebody gives me this opportunity, says, okay, I can give you a magic number, so-called level of information granularity, is your design asset, and you can assign this asset, allocate this asset across the parameters of your network. So you can make these parameters granular with some levels of granularity epsilon 1, epsilon 2, epsilon p, in such a way that you want to accomplish the highest possible coverage of your data, and you have to make sure that you follow the balance of level of information granularity. So in other words, you follow the request that these sum of epsilon 1, epsilon I, and so on, they sum up to n to p number epsilon. So here's just the formulation of the optimization problem, okay? I have some data. Now you've already had your model constructed. I'm not concerned how you did it, that's secondary to me, but I'm going to make it granular. And I want to make it granular by forming granular parameters of the model, so granular weights. Hold on, granular weights could mean that the weights could be intervals, the weights could be fuzzy sets, the weights could be probability density function, the weights could be rough sets. And the request I have is that you maximize the coverage of the data and you satisfy this balance of information granularity. So this is a constraint in your optimization problem. So obviously this is just a formal description of the optimization problem. How we're going to solve it is a different issue. You can engage different techniques, including those methods coming from evolutionary optimization. So here we are seeing this nice linkage with computational intelligence as a unifying platform to cope with intelligent systems. But there is one interesting observation that probably is very intuitive. Namely, if I give you higher value of epsilon, you are going to create a better coverage of your data, okay? Because the interval, let's say this information granulars become less specific, okay? They start covering more data. But you are paying the price for this. Why? Because your outcome is going to be less specific, okay? So here what I'm trying to stress. If you increase the value of epsilon, your coverage is going to go up and your specificity is going to be lower. Okay? So that's again the same situation, coverage and specificity as the two of the requirements that are in conflict. And interestingly enough, next slide, we are going to see an interesting dependency between those two characteristics, between these two. Say, if I take the value of epsilon and I do this optimal allocation of information granularity, I'm going to end up with a granular model that is characterized by a certain coverage and specificity. If I change the value of epsilon and do this optimization and again get a granular model that is characterized by its coverage and its specificity. Now, if I create this plot on a sort of on the coordinates of coverage and specificity, we can notice that the dependency, the behavior of this plot is going to look as shown on this figure in general, okay? So if you look at with the value of epsilon going up, then the specificity goes down, coverage increases. Obviously this curve could behave differently. For instance, you may envision that I could have a certain region, a certain plateau, that if I'm going to increase coverage, specificity is not so much affected, but at a certain point this specificity goes down, okay? So you may ask the following question. So what would be the best granular model, irrespectively of the value of epsilon? The model for which the area under curve is as high as possible, okay? So notice that this gives you a kind of unified characterization of your granular model. But not only that, it gives you a holistic description of the quality of your original model you started with. So I may have one model and I create its granular counterpart and I calculate the area under curve. And I have another model and I can create this area under curve and I can compare this area under curve for these two models. So this will be like these general holistic descriptors of the behavior of the models in terms of the language of information granulars. So in other words, what we are doing, we are really forming a certain category of granular models that are built on a basis of existing constructs. It's very important. I'm not telling that you have to forget the model you constructed. I'm telling that you can enrich it and you can offer a better description of the model characterization by bringing information granularity into the picture. Okay, and here there's a couple of motivation observation, a sort of rationale. The one is something that I mentioned just a while ago. So you want to get a more realistic characterization of the model, okay? The second one, next slide please, is the question of the sort of transfer of knowledge. What I mean by that, you have a situation that you have a system, or you have the model that you constructed on the basis of past data, and you're collecting now the current data. For instance, if you have a problem of project management, cost estimation, each project is unique. So now, if you develop the model for cost estimation in the past, this model may not be an ideal one for the current project. Like in software projects, each project is unique because there are so many factors. So my question is, you have the model from the past and you have a new project. What would you do? Well, some of you might say, okay, no matter what, I'm going to use the model from the past. Yes, that's one of the possibilities, but we have to be very much aware of the fact that this model is not going to be ideal. And God knows how well it's going to perform. So there's a certain risk. Somebody else would say, no, I'm going to discard the previous model. I'm going to use the model on the basis, formed on the basis of my current data. But your data are very limited, and it's very likely that the model may not be constructed. So this is probably not a very good solution. So the third one would be something that you rely on the existing model, but you make it granular model, so you account for the diversity of the new situation vis-a-vis the model that was working in the past. So this granularity of information or granular model is going to be reflective of the new environment in which this old model is embedded. Next slide, please. So that's really what it means. And essentially what I have here in mind is that the past model is viewed as a source of knowledge. So you are doing this transfer of knowledge and the calibration of this kind of modification by this type of granularity allocation. The next slide, please. And granular models could be immediate reaction or could be immediate consequence of the situation when you are going to get a model that is less specific or less constrained or less complicated than the previous model. For instance, next slide please. If I have the situation that I created the model and I consider that for the purpose of my usage today, this model is too complex. For instance, it is difficult to interpret, to understand the model. I'm going to make it simpler, but in order to make it simpler, I'm going to make it more abstract. So in other words, I'm going to engage information granulars. Next slide, please. So here's just a very typical example. If you look at rule-based models, and for instance, fuzzy rule-based models, and I may have too many rules, and somebody comes to me and says, hey, I don't want to see those 25 rules, give me 5 rules that are of a sort of equal value. But there are only 5 rules, so it's easier for me to understand. Yes, I can do that, but because I'm reducing the number of rules, I'm making them more abstract in the sense that, for instance, I can form the condition part in the way that these condition parts include information granulars of higher type. So for instance, you might have type 1 rule-based model, and if you do the compression, you get type 2 fuzzy model. So there's an idea of doing this compression. Next slide, please. Then you might have a question of sort of non-stationary environment. Rather than building a model that changes over time, you can try to account for this non-stationarity by dealing with just a model that is granular. So altogether, if we get to this general picture, there are a lot of possibilities because you are really starting with a category of models, you make them granular, and then depending on the implementation, on the realization of information granulars, you have a number of different possibilities. Next slide, please. So again, the same happens, for instance, for fuzzy rule-based models. Fuzzy rule-based model gives rise to granular fuzzy rule-based model, and here you have a number of possibilities. And there is just another collection of examples here. So you can find that you can take any category of models and you can make these models granular. And then, depending on the formalists, you can talk about different categories of these models. So that really just stresses the point that what we are talking about is quite general. It's quite unified in a certain way. The next slide, please. So hierarchy of information granulars. This is really just the last item on my agenda. And what does it mean? Well, it means that really there is a tremendous diversity of information granulars, not only in terms of the formalists, but in terms of so-called types and orders of information granulars. What I mean by that, just next slide. Information granulars of type 2, or type N in general. What are those constructs? Information granulars of type 2 are information granulars whose description is provided in terms of some information granulars. Intervals are described numerically. Fuzzy sets are described numerically. Probability density functions are described numerically. You have a Gaussian probability function. You have a numeric function, okay? So those are information granulars of type 1. Information granulars of type 2 are information granulars whose characterization is provided in terms of some information granulars. So for instance, if I'm talking about the temperature, these first two lines describe you information granular of type 1, fuzzy set of type 1. Membership degrees are numbers. Now what you see on the lower level, at the lower two lower lines, it's an example of so-called interval valued fuzzy set. Namely, the degree of membership is not a number, it is an interval. A degree of membership could be essentially a fuzzy set. A degree of membership could be a probability density function. So you can see there's an entire spectrum of possibilities. Okay? Why are we doing this? Well, just in a second. I'll tell you about in a moment. Okay? Now, you can talk about information granulars of higher order. What does it mean? Information granulars of higher order, in particular information granulars of order 2, are information granulars which are described in the universe of discourse that is composed of information granulars themselves. So here's an example. You are talking about, for instance, information granulars, the space that is composed of 3 fuzzy sets, low, medium, and high. And what we can talk about, the concept of comfortable temperature, you can see that this is the fuzzy set that is formed not on the universe of discourse of numbers, but formed over the elements that are just information granulars. So those are the examples of those other two fuzzy sets. And if you can keep moving with this. So the main observation that we are going to make here is the following, that if you are doing processing realized in a hierarchical format, this processing naturally gives rise to the idea of information granulars of higher type and or information granulars of higher order. So here's just, I know I'm up, the time is up.
No, the question.
Oh, question, I thought that you tried to meet me.
This is something related with one of the assistants that want to know also. Maybe these higher types of granular could be associated to metadata. In any case, how many degrees of abstractions should we construct, and how? Is any general rule or constraint?
I think I would be careful about general rule because it could be problem dependent. It means how far you can go with increased type or increased order of information granular. Automatically you can do everything. You can talk about type N information granular. But I think I would be very careful not moving too far with this unless there is some motivation. So I'm going to show some examples where.
We couldn't use, for instance, entropy or something like in the shadow theory because as I understand, you are the higher types of granular are close related with meaning and interpretation, and so maybe the information should be higher and more concentrated and in lower levels granular.
It's very likely, but I have not looked into this into details, because it could be an interesting idea to see if you have type 1 information granular and associated entropy, and you move to type 2 information granular, what happens to entropy? Whether the entropy is going to be higher or lower. But again, this may require a careful redefining or careful formulation of the definition of entropy in this case. Because that's, for instance, if you have type 2 fuzzy sets, what would be the entropy of this fuzzy set? And again, I have not looked into this carefully. So that's probably a good point for future investigation.
So the point is here that, for instance, if you are dealing with the issue of data, numeric data, that are type 0 information granulars, notice that essentially we can talk about the numeric space of data, okay? Now, imagine that you are creating information granulars of type 1. So you are naturally forming this granular space of type 1 information granulars. So for instance, this could be the way, for instance, of building these information granulars using the principle of justifiable granularity as an example. But here, if you start moving to the next level, and you are processing information granulars of type 1, and this naturally goes to information granulars of type 2, and so on. So you keep moving and increasing. If you go towards the higher level of abstraction, then you are talking about increased level or increased type of information granulars. So again, if you can keep moving with this, next slide. For instance, if you are dealing with clustering, you can see very nicely that here's the situation. You deal with numbers, you get type 1 information granulars, you get type 2 information granulars, and so on. Here's the same situation, that you are forming information granulars, and then if you want to do the clustering of those, you are describing information granulars of other two. So here's just a kind of illustration. Now, here's just maybe a more direct answer to Daniela's question, where we are seeing these information granulars coming from in terms of this hierarchy. Now, please notice that if you have a single phenomenon and you describe this phenomenon using different models, okay? So you have different sort of perception of reality, you have different models. Now, if you get a new experimental evidence, you ask yourself, what is the outcome of these models? Then obviously you can talk about averaging of the results, which is a very simple solution. But if you want to emphasize the diversity of the sources of knowledge, namely models, then naturally this gives rise to this aggregation that results in information granular of type 1. So notice that here is this elevation of the type of information granular, and this elevation happens because you are dealing with the sort of hierarchy of this processing, individual sources of knowledge. And here's another scenario that looks a little bit different. Namely, here we are seeing that admitting that none of the models is ideal, we create granular models on the basis of the existing sources of knowledge. So this kind of green, and not green, this gray surrounding area emphasizes that you created a granular model. So notice that if you have now the model that responds, model M1, M2, MP, that responds to some numeric data, then the response of each model is an information granular. So you get an information granular of type 1. But now you have to aggregate those information granular of type 1, you get the result of information granular of type 2. So you can see that the higher you move at this level of hierarchy, the higher the increased value, the increased type of information granular you are producing. So there is nothing really nebulous about this. This is a reflection of the formulation of the problem, okay? And, yes, please.
Single numbers are granules of type 0.
Numbers are granules of type 0.
Yes, single numbers.
Yeah.
What are granules of type 1?
Type 1. Oh, granules of type 1 are produced here. If you go back to the previous slide, maybe previous slide, please.
Then, essentially, the information granules of type 1 are shown because you used a number of models. So you got number, y1, y2, yp. So those are numbers. But now if you are trying to use the principle of justifiable granularity out of these numbers, you represent these numbers in terms of a single information granula. And this is type 1 information granula. So this is sort of a reflection of the diversity of the sources of knowledge. And now if you got this one level up, you get type 2 information granula and so on. So again, notice that I'm talking in some general terms. I'm talking about type 1, type 2 information granula. Now, if you like to translate it into type 1, type 2 fuzzy sets, that's fine. That's one of the possibilities. But you can think in terms of probabilities. You can talk about probability of type 1, or you can talk about probability of type 2, namely something that is known in the literature as so-called imprecise probabilities. So in other words, the probability does not assume a value, assumes an interval. So what is interesting that this entire process goes on, next slide, then the next one, please, that you might have a situation that when you have some collection of models, so let's say model, just a collection of models here, collection of models here and here, then if you start doing this aggregation, you can come up with information granulas of type 3. So I'm not saying that type n information granulas are not technically feasible, but I'm very careful to state that there has to be a motivation behind a certain coming with the problem. You cannot engage in this kind of wide increase of the type of information granulas because there has to be a strong rationale behind doing that, okay? That's something that one has to be very much aware of. Please continue. And there is just a sort of linkage, what I was talking about, and big data. Because I think, well, why the term big data is very sexy today, I do believe that, yes, please.
I'm sorry, before you go on. So the idea of hierarchy of types is the solution to the problem of evidence versus specificity.
Well, in some sense, yes, because when you are doing this aggregation, that you are engaging the principle of justifiable granularity. So, as you said, if I'm forming type 1 information granulas, and I'm sort of combining them, I get type 2 information granulas. Imagine that I have a fuzzy set, a collection of family of fuzzy sets. And if I ask yourself, so instead of this family of fuzzy sets, could you give me a presentation of these fuzzy sets? You are going to come up with type 2 fuzzy sets, okay? If I give you type 2 fuzzy sets, I'm saying how we're going to represent them by a single information granula, you increase and say, I can represent it by type 3 information granulas. So this idea of raising the type of information granularity of information granulas is natural to the hierarchy of the processing.
So ideally, the lower the type, the more specific it could be.
Yes, but again, if you have different sources of knowledge, you want to put them together, then, well, a simple example coming from statistics. If you have a sample, what is the information granular that you are forming? People in statistics, they do that, but they don't use the same terminology. Simply what they do, they calculate an average, okay? But to any statistician, average only is just a piece, a part of the story, because what they do, they provide you with a confidence interval for this average. So you see that the result of the aggregation is not a number, it is an information granular, a confidence interval. Obviously, this entire process is realized under some assumptions about the probability density function, because in order to calculate the confidence interval, you are assuming that there is a certain probability density function that is that generates this data, okay? But notice there's the same line of thought, that if I'm doing something going to the higher level of abstraction, I'm forming something that is more abstract in terms of the type of information granular, okay? And now imagine that I have those confidence intervals, and then they are coming from different samples. If I bring them together, then again, that could be like a granular confidence interval. So you can sort of see there's this kind of hierarchy. So coming back to the last slide, hopefully. This is just an example which in fact offers some linkages between granular computing and big data. As I said, big data is quite visible today, and I suppose that's kind of implied by the practical needs, but I think it is probably a very nice alignment between big data and granular computing. In which sense? In sense of a number of these observations. Namely, in the sense of level of abstraction. So what I highlighted here in sort of this gray color is some of the challenges in big data, and offered some answers in terms of granular computing. So huge volume of data and setting up a suitable level of abstraction. Again, information granulars form a natural vehicle to cope with this problem. You are not looking at this this huge volumes of data, petabytes, for instance, but you are trying to get something that is more tangible, okay? Second point is user centricity. It's very important. Big data appear, and this entire task comes into existence because of the fact that somebody wants to take advantage of the knowledge contained in the data. But in order to do that, you have to have this effective two-way communication between the user and the system. Because it's not in terms of numbers, in terms of some tangible entities, namely information granulars. And distributed data processing. I think it's really quite challenging in big data, because you say you have huge data and probably you have to do some sampling of the data and create some local models and so on. Fine, if you do that, you have to be aware of the fact that each local model is a source of data, a source of knowledge, and if you do aggregation, you form information granulars that are reflective of the diversity of your findings. So that's more realistic than just coming up with a simple numerical presentation. And the final slide that deals with the conclusion, and really my intention was to offer you an introduction to granular computing. I'm not saying that I covered the entire area. I try to highlight some of the principles, try to really to show what is new and what is old in granular computing. I'd like to dismiss this type of myth that granular computing is about graph sets. Granular computing is about fuzzy sets. No, there is something more than that, and there is something more general and more attractive, okay? And I'd like to emphasize that, again, the formalism of this algorithmic development is quite enormously visible today, and again, it dwells upon some of the formalism that we've already developed, but also it has to really follow a realization of this number of principles that we discussed. Namely, the principle of justifiable granularity, the view at information granularity as a design asset. So I'm trying to really be a little bit more on a positive side than other people, because people are usually talking about uncertainty. I prefer to use the term granularity, information granularity, because it's more reasonable. I think uncertain has this negative connotation. Information granularity is really trying to emphasize the fact that something does exist with which we have to cope with in an efficient way. And hierarchy of information granulars. And again, to me it is important because while I do believe that some theoretical investigations are important, they have to be vividly linked to some applied aspect. So all this manipulation and all this build-up of higher order, higher type information granulars, those should be activities that are well rooted with, well connected with the existing problems. And with this, I'd like to thank you very much for your attention. I'll be more than happy to take any questions, any comments, any observation you might have. Thank you. And I know very well that I exceeded my time. Probably.
You know, big data is usually processed using databases, data warehouses, and data maps. And my question is, how do you relate all these concepts with the current industry in the database?
Well, I think it's really just a question of two layers, because I think when you are talking about databases, you are talking all these mechanisms of queries and so on. That's fine. That's really just a general asset here that we have. But it's a question of sort of bringing this issue of interaction of the user with this environment. That's really, in my opinion, a critical part. Because as I said, they are just a question of two-way communication. In other words, provide me with the summarization, provide me with the pieces of knowledge that are legitimate in terms of this existing big data. So obviously you are not going to give me the numbers, you are going to offer me some more description at the more abstract level. So that's something that obviously you are trying to build another layer around the existing architectures. I'm not saying that, and I'm not arguing, I'm not challenging existing solutions to us in terms of databases. I'm trying to say, could you try to create another layer as in any operating system? So you can see that you have this layer close to the hardware and you are creating sort of more these conceptually advanced layers. So that's really what the role of granular computing could be. I'm not really arguing that essentially you have to sort of change some paradigms of databases, okay?
So up to now, it depends on the programmer or the user to apply this.
Well, it depends. You need to build this certain interface. So something that the user might have some flexibility, might have some possibility to create, to customize this interface. Okay. Because that's a question of customization. I think we have to admit, not all users are the same, because it depends, as I said at the beginning, and this is the beauty of information granulars, that they are universal in terms of the concept, but they are customizable. In other words, I can look at the same problem from a different perspective. If you are talking about somebody in a sort of, top management, they don't want to see details. They say, well, give me a few lines. What current situation we have, is it right? You have only 2 minutes and you have to convey this very condensed picture. Now, if you're talking about somebody who is in a middle management, well, they need something more detailed. They need a different granularity in terms of time. So I'm not going to see, I'm not interested in the sort of some findings that are valid for the next week. But maybe I'd like to see this like, a time horizon of 2-3 years eventually, okay? So that's again the question of this customization. And as I said earlier, we are not talking about the issue of changing the existing layers. It's really just building on top of existing layers.
As a parallel thing.
It's a panel. It's the next sort of level of processing. Now, it's in my opinion, it's a very open question in terms of the volume of data, because I do believe that if you look at techniques of machine learning, that's very often sort of brought into the picture when talking about big data. I have some hesitation about this, because if you are talking about huge data repositories, to which extent those techniques are going to work, because they are going to eventually, their computational complexity still could be quite high. Don't tell me that you are going to deal with billions of data points while playing with support vector machines. Ask yourself how much time you're going to use. Don't talk about neural network if you have billions of data. I think it's a killer. So what is the solution? Well, one possibility is that don't take numeric data, form information granulars. So instead of billions of data points, you might have maybe thousands of information granulars, and take these information granulars as the entries to your advanced technique of machine learning. You are losing something in terms of the precision, but you cannot have everything together, okay? So now it's a certain trade-off that you are going to develop. But maybe it is an acceptable trade-off, okay? So again, what I'm saying, it's really the question of sort of machine and question of granular computing serving a certain conceptual and algorithmic layer. Something that offers you the flexibility to interact with the user, offers you the flexibility to cope with existing, I think, spectrum of algorithms that have been developed for decades.
Thank you.
Any other question? ¿Alguien más que quiera consultar? Aprovechemos el micrófono, así sale grabado.
If there are no questions right now, I think my email address is available, and I'll be, as I said, very happy to talk, to communicate with you online. Yes,
I have a little question.
Yes.
I would like to know which mathematical formalism is behind this model. For example, first order logic is enough, or higher order logic?
I think I didn't talk about logic at all. I think that I must admit. So it probably could come here in a sort of more formal way. But again, I sort of mainly focus on the formalism that we are cope with, or we deal with when talking about fuzzy sets, rough sets, and so on. So it's more sort of this type of formalism. And obviously,